Hi, everybody. Welcome to our webinar today. Really excited to have you here. My name is Chris Heyer with Aquatic Informatics. I've been in the water space for about 20 years and have spent a lot of my time focusing on helping our customers transform data into information and actionable insights to help guide water resources management. I'm really excited to be here today with Jeremy Testa. Jeremy and I go back a long way, all the way back to graduate school. We're down here today at beautiful Chesapeake Biological Laboratory on the Patuxent River, right across from Patuxent Naval Air Station. So apologies up front for the sound of loud jets flying up and down the river. Jeremy's been a longtime colleague and a friend, and he's currently professor here at Chesapeake Biological Laboratory, which is part of the University of Maryland Center for Environmental Science. Jeremy's research really focuses in on coastal marine ecology, with an emphasis on eutrophication processes, nutrient cycling, dissolved oxygen dynamics, and ocean acidification. And as we've often talked about, these are critical issues not only here to the Chesapeake Bay and the Patuxent River, but also globally. Jeremy's team has been doing some amazing work down here at CBL. And actually, it's been highlighted in this month's Stormwater magazine with a nice article and a write-up. So I'm looking forward to digging in a bit today, Jeremy, and going more in depth on the article.
Thanks, Chris. Happy to be here.
Yeah, awesome. So we have a bit of an agenda for you today. We're going to talk about the Chesapeake Biological Laboratory and the history of the Patuxent River, get into how technology impacts CBL and the broader community here in Maryland, really focus on how we unlock the power of data and provide value to local aquaculture, ecological restoration and ecosystem restoration efforts, and the public in general. We'll talk a little bit about the future of CBL's water monitoring and have plenty of time for questions and answers. So there is a question and answers Q&A section of this portal. Feel free to type your questions in there. We'll try to get to as many of them as we can by the end of the webinar. And anything we don't get to today, we'll follow up with you on. So maybe we'll start with talking a little bit about the history of yourself, Chesapeake Biological Laboratory, and the Patuxent River. And maybe we'll start with the river in the area.
Great. Yeah, for those of you who are maybe not familiar with this region, the Patuxent River kind of starts in and around DC, its watershed, Washington, DC. And this is a system that's traditionally been a very productive seafood estuary. There's blue crabs are part of the seafood economy. Oysters have traditionally been a part of the economy. And Chris and I saw work boats sort of coming into port right behind CBL here. And it's an interesting place because, you have all this seafood production in the estuary, but it's also a watershed that was at least formerly highly agricultural, including a lot of tobacco production in the region.
Yeah, I was just in Denver last week, and one of their featured menu items were Chesapeake, Virginia oysters.
Excellent.
Right. So even still today, it's an important part of the aquaculture and fisheries that happen globally.
Right.
Yeah. So, tell me a little bit about what this ecosystem was like, maybe back at the turn of the century, what the early settlers would have seen when they were here, compared to maybe how it is today.
Yeah, there's a couple of historical references that people often use to think about the Chesapeake Bay. So at the time when John Smith was first exploring the area, an Englishman, pre-colonial times, a lot of the reports that he gave and a lot of the artwork that was done really showed this not only productive system, but a system that was really benthic oriented. There was this clear water, and the Native Americans were sort of fishing like in the shallows, and it was a place that was kind of the bottom of the bay, and the shallow waters were blanketed by these underwater plants. And a gentleman named Hungerford that actually escaped what I think was a cholera epidemic in Baltimore, of all things, came down to Calvert County, which is one of the counties on the north side of the river, to kind of escape that epidemic. And he wrote a book while he was here. And one of the quotes from that book describes him looking out into the river and seeing the Finny tribe, which was this school of fish, and he could see the bottom in 20 feet of water. And
that's crazy.
Today, you can probably only see the water in 5 feet, or see the bottom in 5 feet. And so, over time, as we've used more fertilizers as human populations have grown. The Patuxent, much like the greater Chesapeake Bay, was degraded, and some of those aspects of the degradation involved, those fertilizers fueling the growth of algae in the water column, kind of making it a lot less clear, more sediment cutting off the land. And we've seen those grasses that once blanketed large parts of the Patuxent not entirely disappear, but in many parts of the river really go down.
Yeah, it's tragic. So for those not familiar with the area, Calvert County, which is where we are, is a peninsula, and it's bordered on one side by the Patuxent River and Chesapeake Bay on the other. And a famous senator from here, Bernie Fowler, has his sneaker wade, right? Where he'll wade in and see how deep it is before he can no longer see his bright white sneakers. And there's been some improvements in recent years with the restoration efforts, but by and large, it's nowhere near the 20 feet that you talked about early on.
Right. And these plants and the clarity right around CBL is something that has been traced by photography, which we'll get to see some of later.
I think we have an image here actually too.
Yeah, so if you look at this picture, you can really get a sense of that picture on the left, which is from the 1930s, 1940s, where there's just all that darkness you see flanking the island, where all these plants growing on the bottom. And that most recent picture is about 20 years old, from the late 90s. And you can still see that shoal there, and you can see our research pier, which we'll talk about as well, sticking out into it. And those grasses disappeared in the late 1960s, and except for a blip, we haven't really seen them since.
Yeah, it's tragic. I mean, that image on the left is so clear with those patches of seagrass, those dark patches that appear there. Yeah. Well, that's some good history about the Patuxent River and the Chesapeake, but talk to me about the importance of Chesapeake Biological Laboratory in the region.
Well, Chesapeake Biological Laboratory is the oldest publicly funded marine institution in the country, one of the oldest. And so it started in 1925, and it was founded with its first director, Reginald Truitt, who's sort of established the lab to kind of study, which was kind of novel at the time, the biology of crabs and oysters, how that related to the physics and the chemistry and the biology of the water, and how learning about all that would help us better manage those species. And so that mission of CBL and UMCs in general, of doing science that has an immediate translation into maintaining resources and supporting public policy, has always been part of our mission. It's sort of science for environmental problem solving. It's been one of our pillars of what we do. And so, one part of that has been to do monitoring and to do research, not only right in and around our laboratory, but in Chesapeake Bay broadly, and then all over the world.
Yeah, we've talked before about this concept of Chesapeake Biological Laboratory being a translator of science for the general public. And I know currently you host a lot of public seminars and webinars. Talk to us a little bit about how the lab plays that translation role in educating the general public on science.
Yeah, so we do this in a lot of different ways. So one way is to just host seminars where we can give presentations, like you said, to anybody that lives in the community that wants to learn more. People like myself and my colleagues, we sit on panels and we sit on work groups at, for the state agencies, for the federal agencies, and, basically try to translate what we know into how they might manage the landscape, how they might manage the blue crab fishery. And so there's a lot of ways where we do that. And we also, a lot of us live in the community, and, we have collaborations with, people that we know that work, I have collaborations with friends that work at the nuclear power plant that's up the river. We work with, watermen, and we work with aquaculturists that are working in and around CBL and in the region as well.
Yeah, the CBL has always played that role of helping sustainable water or natural resource utilization, right? So I think back to the construction of the Chalk Point power plant and all of the fisheries work that happened back then around impingement and entrapment and temperatures and the impacts on young fisheries and juvenile fish is a pretty critical piece of history for Chesapeake Biological Lab to ensure that those natural resources utilizations are done in a sustainable way that don't have too big of an adverse impact on the natural resources.
Right. Yeah, very much, there's almost that duality of what we do, which is in some ways trying to make sure, our society can sort of live and thrive and do it in a way that's least impactful as possible. But also that there's ways that science can sort of support, economic activities, to make them more efficient or to bring them real tools that help them have some awareness of what's coming down the line or things like that. So,
well, that's great. So maybe we'll just switch gears to personal. So your graduate work was at sister laboratory, Horn Point Laboratory, master's and PhD. What made you decide to stay in the University of Maryland system and stay a part of Chesapeake Bay research?
Well, I think myself, like a lot of people in our institution, we were always interested in, being outside in natural systems, but we were interested in the process of science and the discovery of science. But we also wanted to put that science to work to, lack of a better statement, to make the world a better place, but maybe just help inform sort of real problems that are related to, people's daily lives. And, UMCS is really an institution that encourages that, it rewards that. And so it's the type of place that I want to be to do research.
That's awesome. I love this idea of helping people improve their daily lives. So let's talk a little bit about, how technology has impacted not only CBL, but the broader community. And this image we're looking at on the screen here is from your current data portal, WebPortal. But what I love about this, maybe you can speak to it, is the likelihood of sea nettle presence. So why is that important, and how did you get to being able to display that?
Yeah, what's interesting, before I get to that, it's always been something where when we saw the web portal, our original idea was, well, this is the way that we're going to put all the information we're gathering here, like, out into the public sphere. Yeah. So we always saw it as an outward looking part of our program. And so sea nettles, for those of you on the call who maybe don't live near the coast, there's a stinging jellyfish that lives in Chesapeake Bay and up and down the eastern seaboard. And it turns out you can have a reasonably good way to predict how likely you are to sort of be in the water when a sea nettle is there, just by the salinity and the temperature of the water. And colleagues of ours sort of developed those relationships. But once we had sort of real-time salinity and temperature data being collected off of our pier, instead of doing that kind of using a numerical model or some other piece of information, we had real data that we could QA, QC in real time that could make that prediction. And it really sort of was one of the main ways that we could take what we were doing off the pier and put it out there so people that wanted to come and swim in the river might have some idea how likely they are to get stung.
That's really cool. It's a small example, but it does speak to the power of leveraging data and science and outreach to inform the public. So what are some of the other ways CBL is doing that today?
Well, one of the ways that we've been doing it recently is that in part of our system, we're monitoring aspects of the water, but NOAA also has a tide station out there, the National Oceanographic and Atmospheric Administration. And so they're collecting all sorts of physical information. And one of the things they focus on is, tides and water level. And so CBL sits on this peninsula, as you saw before, and there's two roads that come to the end of it where our laboratory is. One of them is nearly at water level. And so when we get a particularly high tide, water starts spilling through a culvert out into the street, and you have salt water there, so you probably don't want to drive through. And so we were able, through a bunch of observations, to identify at what water level out on our pier would be associated with water coming up into the under the street, and sort of give people an alert if they were going to come down there. And one of the things we discovered just a few weeks ago is we had one of the biggest storm surges that has occurred since 2003.
Since Isabel, Hurricane Isabel,
and flooding Annapolis, Virginia, all up and down the Chesapeake Bay coast and other places. And this picture you're looking at here is, from kind of the peak of that flood event. And we kind of discovered that there's another threshold that we can build into our system that, goes beyond just when there's water there, but tells you when the road is more or less impassable, which there was 1 to 2 feet of water out on this road at the peak of that storm.
Yeah, that's really powerful to be able to do that and translate that to something that, the common public can understand and appreciate every single day. Yeah, and I think CBL has also been really good at communicating the impacts of global climate change as well, and the rapidly warming trends that we're seeing. I'm always impressed by when we drive in, and I think we have an image of this later, the time series of temperature data collected here, because you've been collecting data for a long time out here at the pier, right?
Right. We our director, our original sort of founder, Reginald Truitt, sort of worked to establish a program starting in 1938 where somebody would walk out to the end of the pier at noon every day, even on the weekends at the beginning of the program, and use sort of traditional kind of handheld equipment to measure salinity and temperature. So like a hydrometer that you could imagine if you're those of you who've brewed beer, helps you get to the density of the water and you can compute salinity, and then just using a mercury thermometer. And that program sort of has persisted practically uninterrupted until this today. And it's one of the longest sort of continuous temperature records in tidal waters that exists anywhere in the world.
Yeah, that image, and I apologize, it's not up on the screen right now. It'll come on later, but it is powerful to see how temperature has deviated over the course of almost 100 years. And it's really hard to argue that there isn't an impact in the most recent, couple of decades on water temperature.
Yeah, one of the things that reminds me of is, there are, oyster aquaculture operations happening just outside of CBL in and around our pier. And although that warming record in and of itself may not be that informative, there's the potential that by knowing salinity, temperature, pH, and how much chlorophyll or algal materials in the water, these are all conditions that those growers can use to understand when and when not, their operation, might be vulnerable to some sort of environmental change. And so around here, one of the big issues is when you get really strong freshwater flow events, the salinity drops down and oysters either stop growing or worst cases, there's some mortality. And we had one of the largest precipitation events in the region just a couple of years ago. And the grower just outside here, had pretty substantial sort of, loss and or lack of growth. And we were able to see and track, that salinity drop and how long it persisted. And, really kind of start to think about tying that to what people are doing commercially on the river.
Yeah, it's really important. And, it guides restoration as well, right? So there's the commercial aquaculture aspect of it and guiding that, but also overall restoration efforts that are happening in the bay. I mean, there's millions of dollars spent each year on trying to restore oysters and SAV to the bay, and understanding how those temperature and salinity impacts and the changes in temperature and salinity will impact those restoration efforts is pretty critical.
Yeah,
I would imagine.
Good.
So let's talk a little bit about data. So the lab's been collecting data for almost 100 years. I remember when we first started talking, it was sort of all over the place, including boxes in some places. What's the main reason for trying to consolidate all that data into one place?
Yeah, well, for one, there's just a housekeeping kind of aspect to it. But that housekeeping has a real purpose, right? So, now we have all of our data that has been collected off the pier, which just isn't just salinity and temperature. It's all this new sensor data we're collecting.
Right.
It's all this physical data that other agencies are collected. It's kind of hand grab data that we make every couple of weeks and other people make periodically. So once all that system data is in one place, it really gives us sort of the capacity to put it together to do interdisciplinary work, which is kind of a lot of what I do and what my colleagues do. And so, having all that data in one place, it allows us to do analysis, but it also sort of encourages collaboration because, everyone has a role in getting this data sets together, and therefore they can sort of see the mission of doing more with it.
That's really cool. And you're pulling in other data sources today, right, from federal cooperators?
Right. So we have, tide and wind information, which, we bring in with some of our biological and chemical measurements to try to interpret that. We bring in data from the U.S. Geological Survey on their freshwater discharge into the Patuxent. So when we see things happen, you can, it's on our portal even, you can even see these relationships happen in real time.
Yeah.
So you see the ball, the peak in the hydrograph, which is, miles upriver in buoy. Right. And then you can just sort of wait a few days and you sort of see that, the salinity start to drop. Sometimes you can see the chlorophyll go up because the algae are sort of growing in response to that. And we've used it for our research, looking at our current velocity data, right, and understanding how those currents might impact, how food is moved around in the oyster farm. So there's just all sorts of capabilities that happen when you get all that data together.
Yeah, that's good. I know that CBL isn't responsible for sort of routine monitoring, but certainly the idea of that guiding adaptive sampling and adaptive monitoring. And I know even within your own research programs, you've been able to leverage that upstream data to plan out when you need to, mobilize and start collecting more data to guide some of the research that you're doing.
Right. And you're right. Even though we don't do monitoring per se, that's not part of our mission. The fact that we've established this for our own purposes, allows it to be used, for other monitoring purposes. Like we measure dissolved oxygen in real time, and the Chesapeake Bay has a big problem with, having very low oxygen.
Yeah.
But for the most part, it's in the deepest open part of Chesapeake Bay. But even oxygen at somewhat, even moderately low levels can have impacts. And we sometimes see those happen out here on the pier, even though it's only, 6 or 7 feet deep. And so it actually, builds more understanding of what's happening outside of the places that, the agencies are monitoring.
And I think a lot of that work has helped guide the agencies to their long-term monitoring programs. So if I think back to Maryland DNR's shallow water monitoring program, for example, the Scientific Advisory Committee, which was made up largely of university researchers, helped guide a lot of the science behind that monitoring program and that long-term impact.
Yeah, exactly.
Yeah, good. So this is great. We're consolidating data for 100 years, being able to understand trends and impacts and correlations, working with other agencies. What's missing? What data aren't we getting that we'd like to get today?
Yeah, well, I think it's probably true. We're always going to be, missing data and not have things. But I think if there's one thing we're missing, it's probably trying to relate what is happening in the environment and how organisms are being affected by that kind of in real time.
Yeah.
So we have these notions that, poor oxygen conditions, maybe impact fish growth or they limit where they can feed. But we don't necessarily have kind of co-located information on that. And, the system that we have, may never be able to solve that problem. But the fact that we have real-time information, and if you can think ahead to, being able to sort of track the movement of organisms by this pier and know like what conditions were happening when they did that, that would be the type of thing that we can do.
And there has been some fish tagging work, I think, that's happened out here as well, and trying to tie that together.
Right. And one of our colleagues listens for, marine mammal calls as well. And they've had their instrumentation out there as well. So there's multiple ways and there's been, since people have been looking for dolphins in particular in our region, my colleague Helen Bailey's team, has a citizen science program, that
right.
sort of looks, people sort of report where they see dolphins. And there's been this sort of almost explosion in people's sort of recognition of dolphins being around. But, some aspects of, where they are, when they are, what they're doing is, that those types of studies can be supported by the kind of monitoring systems here.
Yeah, I think it's become not only that sentinel station for that long-term historic record, but that testbed, if you will, for innovative technologies and how we can incorporate them into long-term monitoring programs.
Right.
Yeah. And I think we talked a little bit about the sea nettle likelihood, the presence of sea nettles. I think that opens a door for surrogate measurements, right? So things that are difficult to measure with sensors, but where you might be able to draw correlations to parameters that are easier to measure. Mm-hmm. So I think about nutrient loading and eutrophication and some of the main aspects of your research and how you might be using some surrogate signals to understand when nutrient loading may be highest.
Yeah, we do that sort of in a number of ways. Some of them are seem like more esoteric academic things, but others are more practical. And so, like, for example, by having an oxygen signal, you can sort of, because plants kind of produce oxygen when they photosynthesize and they take it up when they're sort of breathing out, exhaling. If you look at an oxygen signal going up and down during the day, so the sun comes out, the oxygen goes up, the sun comes down, it goes down, you can kind of quantify, how much photosynthesis and respiration are happening in the system. And it turns out you need the tide information and the
Right.
wind data to kind of correct that signal. But then when you have that, you sort of understand this rate of how much the plants are growing. And that's really one of our main metrics of how much nutrient loading is polluting the system.
Right.
And we have models that we run that simulate how well oysters are growing. And by having that real-time signal out there, we can basically, use the model as like a data analysis tool and have us sort of predict oyster growth just by what we're measuring on the pier.
Yeah, that's really critical. And, I think we talked about the aquaculture impact and the ecosystem restoration and tying all of that together, including into fishery management and management of the dissolved oxygen issues in the bay. So talk a little bit more about the dead zone. As I understand it, it's at least in North America, only second to the Gulf of Mexico dead zone. What are the impacts of that, and how are some of the research guiding better water resources management to prevent that in the future?
So the dead zone in Chesapeake Bay, what we call the dead zone, which is really kind of a misnomer because it's, there's plenty of life that lives there, but it's sort of microbial life, and it's kind of deprived of, the benthic worms that really support the food web. And
Right.
lots of fish primarily will avoid that. And it's a big part of Chesapeake Bay's sort of main body, especially in the deeper waters. And, it's probably kind of a natural feature of the bay. The bay is certainly vulnerable to this because it's the way the bay waters moves. It's almost this like circulation that sort of has this deep water in the bay that kind of stays there for a long time.
Right.
It's collecting all this material, and the bacteria break it down and they consume oxygen when they do that. And the more nutrients are coming to the bay, the more plants are growing because of those nutrients. All that material sort of finds its way into the bottom. It gets broken down, consumes oxygen, and then there's really no source of oxygen to those waters.
Right.
They're dark, so there's no algae producing the oxygen. And the way estuaries work is you have kind of this fresh water on the top, salt water on the bottom. They kind of create these two layers, and you don't mix that oxygen
Right.
from the air down to the deep. It's almost like oil and vinegar. And so, that's a pause for a minute while the F-35
one of the jets
flies overhead.
I remember when they were doing the engine tests for the Super Hornet, and this place would just shake all day.
Yeah,
and 6 hours a day.
There are some quiet days here, but there are some days where there's a lot of action.
All right, so we're not able to get the mixing that you would normally get at, say, a lake, for example. Yeah.
And I think there's one of the main sort of targets of the bay restoration. We're trying to get the waters clearer, right? And we're trying to get more grasses back. We're trying to get more oysters back. But one of the other things is to get oxygen levels higher wherever they can be, because those oxygen levels are really just like we need oxygen to survive. All the organisms that live there need to survive. And it's one of these. So having data, and more data and more high frequency data are one of the ways that we can kind of understand this dead zone problem better, because typically we understand it by sort of taking a snapshot of what it looks like every month or so.
Right.
And, the winds blow and river flows come in from the Susquehanna and other rivers, and the system's just changing all the time. And, we can be biased by just taking a snapshot every once in a while. So these real-time systems help us to do that. And like I said, even though out here, for example, and in other shallow waters, you don't have that sort of dead zone problem necessarily. Right. Under certain conditions, you can't have the oxygen dropping down at night when there's no phytoplankton or algae growing. And that's important for habitat too. It's part of how the restoration goals are measured. And
Yeah, no, I remember, my early days here in the Bay, and the idea was before continuous monitoring, we didn't have a lot of low dissolved oxygen issues in shallow waters because guess what? You're out there at 2 o'clock in the afternoon every day, you're sampling, photosynthesis is at its peak, so oxygen levels are high, but every night those oxygen levels are dropping to hypoxic and anoxic conditions. And so that really changed the thinking of the science in the bay. And I think tying it back into the landscape and water restoration, one of the guiding factors has been, correct me if I'm wrong, but I think it's been on impervious surface and the impacts of development on the landscape and the impact that has on the watershed and the water itself.
Yeah, and it's, the thing that is true is that everything's always changing. So there's the change that we're trying to envision through action,
right?
Maybe to help reverse some of these pollution problems. But then there's change that's going to happen because people are moving and there's development happening. There's change is going to happen because of, both natural and man-made features of the natural environment. So, tracking that change over time and how we sort of glean out the signal that we're interested in or the target we're trying to reach among all of that change and all of that variability is one of our biggest sort of challenges in trying to manage tidal waters. And that's where data helps.
Yeah, you can't get there without the sensors and without the data and the tools to process that data and interpret it and understand it. Yeah, well, good. So let's talk a little bit about now moving to the next phase, which is we're collecting data, we're managing that data. Now we want to forecast with it. We want to understand what the impact would be on all sorts of things, and how do we build better tools, and why is that important in order to help us forecast some of the challenges that may be ahead of us?
Yeah, well, I think it's one of the things that a lot of different sort of entities in government and in the academic community and in the private sector have latched onto is how can we do better at forecasting the marine environment? As everyone knows, weather forecasting has gotten better and better and better over year.
Most days.
Yeah. Whenever I say that, people look at me and like, oh, really? But, if you statistically, weather forecasts have gotten a lot better and people build their lives around that. And so, what's holding us back from doing that in the marine realm? And some of it's investment, but some of it's, having the tools to get there. Yeah. And so, there's plenty of forecasting in the marine environment that happens through, really complicated, complex numerical models, to predict storm surges, right? To predict salinity, even to predict dissolved oxygen. And another way that we can go about thinking about forecasting is to just use data streams, right? And, the new statistical tools that are emerging allow us to, maybe get better at predicting those things. So, for example, we've been working on a project here using our salinity record to try to predict salinity and forecast salinity, 3 days out, 4 days out, not using any environmental data or not using any external environmental data, just using what we know about what the salinity's been like before. Because it's like, well, who would use that? Well, one possibility would be that you have someone that's managing sort of intake for an oyster hatchery.
Sure. Yeah.
And so if they have 3 or 4 days warning that there's going to be a really low sort of salinity period, they might be able to adapt to that. People that are growing oysters right out there probably can't adapt to that. They just have to grin and bear it. But there's also the capacity to sort of predict things like pH. And so you might have an idea if there's going to be a low period in pH, which might be harmful to oysters as well. And so I think there's a big opportunity to sort of take these real-time data streams that are growing and the different variables that we're measuring and sort of put them all together.
Yeah, it's good. And you can even take that back to more of the municipal space where if your source water is natural environment and you have capacity for storage and there's an event coming and you're able to predict a low dissolved oxygen event, a high turbidity event, a big pH change event that might impact your treatment capabilities, and you can pivot to your stored water as opposed to your source water. I think that can be powerful as well, making that connection.
Definitely. There's oyster growers in other parts of the country that collect real-time information, and they just manipulate the chemistry of their water when it's not what it needs to be.
Right.
And so by having sort of real-time sensor data, they have the capacity to do that.
Is there work being done here at CBL with machine learning and data science and trying to bring that into this aspect as well?
Definitely. We've used various machine learning algorithms to do this salinity forecast, and we've done it for salinity, but we envision taking the same sort of framework using machine learning to, predict pH, right, and to predict the potential for low oxygen event. And we could do that just by using what we've measured right here at the pier, but by bringing in the freshwater flow from the upper part of the Patuxent estuary, for example, we have another piece of information that's probably going to help us better forecast what's happening out here.
Yeah.
And so all of these tools are meant to sort of give, people, working and growing around here, more information. And whether or not how they apply that information is still, unclear and probably up to the user, but at least we're trying to provide the tools.
Yeah, and I think the one thing that's clear is those tools require data, and so the importance of bringing the data into them. Well, that's good. So, maybe as we wrap up here, and I want to remind everybody that if you do have questions, please go ahead and put those questions into the Q&A tool, and we'll get to them in a moment. But if you think about the journey that you yourself have been on and the lab here, from 1938 to today with data, with trying to interpret data and use it to guide management actions, what advice would you have for people who are maybe just starting out? Maybe they're drowning in data, but they lack that information that they really need to make more informed decisions. Any advice for them?
Well, I think, depending on, who you are and depending on what you have access to, building a team with different expertise is important because, I only have so much capacity, it's not only a matter of time, it's a matter of what's the expertise.
Right.
And so, I'm collaborating with a statistician to do this forecasting. I'm trying to collaborate with, oyster growers to understand, you have lots of data and you can do lots of things with that data. But to what end, right? And so it's almost sort of like, maybe if you sort of work for a municipality or something, it's very clear, what the outcome is, but if you're sort of in the academic world, right, or maybe in the management world, understanding exactly what product you need, and that's going to have the outcome that people will use, I think is one of the challenges.
And that idea of specialization doesn't just apply to how you work with the data and interpret it, but also how you manage it, right? So you had started out running Aquarius on-premise on your own servers and managing updates and upgrades and et cetera. How did that go for you?
Well, it was a challenge without any additional expertise in-house. And so it was transformative to be able to have, a cloud solution where we didn't have to manage that. And we could just focus on the data, and the sensors, which in and of itself is a major sort of challenge to just keep going too, and having, the real-time data. Another nice thing about it is we look at it all the time.
Right.
And so if something's going wrong, we know sort of right off the bat, and we can go switch out a sensor if we need to. We can go, try to understand, what might be going wrong. And, we sort of do that kind of regularly. Sometimes we see something odd, and it just happens to be that one of the fish that like to occupy our pond have sort of chosen to sit on the sensor for that one period.
Right.
The turbidity goes way up, or something happens. So
yeah, and I remember, kind of a softball question, I suppose, but I do remember when you made that switch from on-premise to cloud, and our conversation changed from, oh my God, how am I going to manage these updates, to what other data sources can I bring into the system, and how can I leverage the system now to get more out of it? So I think that was transformative for the lab to be able to make that switch.
Definitely.
Yeah, cool. Well, thanks, Jeremy. So maybe we'll pivot over now to some questions and answers. This was really good to have this chat. I always enjoy talking to you and talking about local issues here in the Chesapeake Bay. We'll dig in a bit. Pardon my eyes. I'm trying to see the other screen with the questions. So one of the questions here is, as you think about maximizing different data sources, maybe just recap on some of the publicly available data sources that you're pulling in, and how easy it was to get them into your system.
Well, when we first did it, I think we had some help, but there's so many tools out there now to pull data off the web, and many they were really done within the Aquarius system by help we got through Aquarius.
Right.
And so, but I have other colleagues that we routinely pull these data streams in. So moving forward, we think a lot about, like, okay, what's that next sensor we could get? But it would be expensive. It would be difficult to maintain. And the truth is, there's lots of relevant information that's already being collected out there that we can pull in. So one of the things we haven't done yet, for example, is local precipitation data.
Right.
They're real-time records, and we're not pulling them into our system, but they would be just as relevant as the freshwater flow data we're getting, for example.
Publicly accessible data, so it should be easy to pull in. Yeah, good. Some questions here about community use of data. So, we talked about the presence of sea nettles, the likelihood of sea nettles, and people being able to use that for swimming. We talked about the flooded roadways. Are there other things that you have found through your community outreach and how citizens are using the data?
I think it's been one of the challenges for us to get a sense of just how widespread use is. I have some personal friends that use the data all the time. They like to fish there, right? So oftentimes they're trying to get a sense of, what the water level is there, because that's relevant. Sometimes they give me feedback on the accuracy of the sea nettle forecast. So if you think weather forecasts have their issues, sea nettle probabilities have some issues too. But you can't always see them when they're there, because they like to go hang out at the bottom sometimes. And I do know that there's people in the lab, that use that data, not necessarily because it's a central part of their research, but maybe they're using a seawater system here, and and they wanted to get to it. So I think it's one of the things that we need to improve upon in the future, is trying to survey out to the community to understand what people are using and why, and therefore encouraging us to come up with new tools.
Oh, that's good. Yeah, that's good. It's really good. Yeah, and I remember back my days with Maryland DNR when the program, and I think it still operates this way, would basically do a 3-year revolving study in an area. So you'd have an set of instrumentation in place for 3 years, do your assessments, try to capture wet and dry years, and then move on elsewhere, just to control costs, right? It'd be difficult to manage the entire Chesapeake Bay watershed all at one time. And we learned pretty quickly that there were people who were using the data that we had no idea were using the data. So as you mentioned, fisher people who were out there looking at dissolved oxygen and temperature all the time. And it's interesting that you start to measure that impact when you take something away, as opposed to when they're using it day in, day out. Oh, that's good. Sorry, I'm just trying to, there's a lot of questions there. I just can't see them. I have to scroll. Forgive me. How much effort do you think has been saved by leveraging software versus sort of doing something yourself and building an in-house solution?
Well, I think it's saved a ton of time and effort. It's hard to put a number on it, but it's substantial, and I think it just builds a community even within our own institution around the data by having it be readily there and usable. Okay,
that's good. So here's an interesting question. So this person's actually jumped on your website during the call, and they noticed that you're defining sort of low, medium, and high values for a lot of your parameters. So how did you come up with those thresholds, and have you applied them everywhere?
I think a lot of them were they're split, I guess. There's a group of them that we kind of decided upon just by doing a little bit of analysis of the record that was there, right? So, for example, the flow, we kind of have an idea of what, the upper 75th percentile flow is, right? And so we call that high, we call the lower 25th percentile low.
Okay.
Everything else is kind of in the middle, right? So there's kind of like a technical decision. For things like dissolved oxygen, we kind of focus on these thresholds that like have environmental relevance on them that we kind of use in the local management here.
Okay.
And so it's sort of a combination of that. And I would sort of, the short answer is kind of like some combination of what other people are using because they have real biological value and just local, kind of quote unquote expert opinion.
Okay, fair enough. But still data driven, right?
Yeah.
Not arbitrary. But the flexibility is there to change them how you see fit based upon local conditions. So we talked about the local roadway that floods, and certainly putting that into a stage of minor, moderate, or major flooding event is easy to do.
Yeah.
Or maybe in terms of what the public could understand, caution to drive through, don't drive through.
Right.
You're
exactly.
crazy. We're calling the rescue team for you now.
Exactly.
So that's good.
I think that would have came close to happen.
Okay, so just looking through here, some other questions. Have you received a lot of requests for information from other educational institutions on your program and how you put it together, and others looking to emulate what you've done in terms of public outreach?
Yeah, I would say that one of the things that we've tried to do, and I don't know if it's been a roaring success, but there's at least been a little bit of interest, and is that we've built some activities for local high school students where they could log into our system because it's there, download some data streams, and then do some basic calculations with them.
Yeah.
So like in a physics class where you might be interested in how light is taken up or scattered in a water.
Right.
You could take, we've created a lesson where you can take data streams here and sort of calculate, on any given day, how that loss of light in the water column would happen. And so
cool.
We've made an effort to try to push the system out on the local community for education purposes in that way.
That's so critical, right? I mean, it goes beyond education to shaping and molding the next generation to be stewards of what is a very limited resource. And if we ever have a hope of getting back to what it was once like for John Smith and the early settlers and the early Native Americans, that's where it has to start.
Yeah, and I think one of the things that we probably that any group I think could do is advertise.
Right.
I think one of the, if there are, like you said, maybe we don't know how many people are using our system,
Yeah.
but by repeatedly advertising it, it's just getting it into the minds of people that this is out there.
Yeah.
And it's going to be useful. Maybe not every day,
Right.
But there's going to be a time where you might want to go look at that data stream, and it's just keeping that in their consciousness for that.
Oh, that's good. There's a question here. We talked about that Solomon's temperature time series image. Thank you, Rhett. Rhett behind the scenes here, making sure everything goes wonderfully. So what you're looking at here is actually, it's metal, right? It's a metal sculpture, if you will.
Yeah.
It's a metal sign, a metal sculpture that's at the entrance of the lab. And it's, when you see it in person, it's super impactful. But even here on the screen, can you just walk us through at a high level what we're looking at?
Yeah, so this is, we call these climate stripes.
Mm-hmm.
And it's an idea that we didn't come up with, but one of our colleagues here, Laura Lapham, was on her sabbatical in France and had seen this used and thought, oh, we should bring that to CBL. And our lab director, Tom Miller, sort of ran with it, worked with our facilities team really to build this. So we built this thing more or less all kind of in-house. And really what you're looking at here is, a coloration of the temperature for each year, going back to 1938, where the blues are cooler and the reds are hotter. And I think that picture sort of tells you everything. Yeah. And it's, Solomon's is a place where a lot of people come to be tourists. And, that's an opportunity for us as an institution to take advantage of all that foot traffic. To give messages out that might otherwise be difficult to get there. And so I think this is just phase one of how we're going to try to communicate in this kind of way.
That's great. I mean, I think that's so critical to help inform the general public about, what are difficult and complex pieces of information, and how do you boil down data into something that's easily consumable by the public?
Exactly.
That's super impactful. It's a beautiful sign. Okay, I guess maybe we're at time and we'll wrap up, but I think you provided a couple of photos. So, let's be a bit, Yeah, there we go. So help us understand these couple of photos that you provided, and then we'll wrap up today.
So I will admit that I don't know the exact storm here, but this is a picture of the pier.
The original pier, right?
Yeah, going back at least 5 decades under one of the big strong storms that occurred here, and
maybe Agnes or something like that. Yeah.
And it's, this picture is almost exactly what it looked like 3 weeks ago when we had that storm roll through here. So
this pier was a little lower to the water, if I remember correctly, than the new pier.
Yep.
Yeah.
And it also had sort of planks. So this is what the pier looks like today. And for those of you who might be interested, one of the nice things about it is it's, instead of having wood planks, it's kind of this grid.
Yeah.
And so the grid lets water come up through it. And so it came through that storm almost untouched, where in previous storms, the pier really took a hit. And the picture on the right there is, you can see the towers. Those are actually NOAA's weather station. And right above that pier house is where we measure photosynthetically active radiation. So it's another part of our data series, is measuring sunlight.
Which is critical for the SAV restoration work that's happening. Yeah. That's good. If you go back just real quick for me, Brett, to that picture. So just for context, this is not the ocean. This is a river.
Yeah.
So, while we're near the mouth of the river, I mean, that looks like open ocean water, but clearly not. So yeah, it was pretty crazy. Well, good. And I think maybe there's a closing shot of the Solomon's Island Bridge. Yeah. And the sunset. So beautiful picture here as well. And I think that bridge is going to be replaced in the not too distant future.
Yeah, it's a beautiful, really, you notice how high it is. It has some of the greatest views of Southern Maryland.
Yeah.
And maybe that's part of the problem, because it's a distraction.
It's a little 2-lane bridge.
It's a little too narrow. And so, yeah.
Yeah. And do you know why it's so high?
Well, I think the original reason was to allow certain ships to be able to pass through it.
Navy ships, I believe, right?
Yep.
Yeah. So, which have there's a small base upriver. So good. Well, Jeremy, thank you. This has been a lot of fun. I always enjoy talking with you, and great pictures. Thanks for all your help in providing those and putting together the visuals for today. We'll do this again sometime.
Sounds great.
All right. Excellent.
It's fun.
Good. Thank you, everybody, for joining us.
Bye-bye.